The battlespace geometry dictates that an engagement between a fourth-generation F-16 Viper and an F-14 Tomcat is decided entirely by absolute energy maneuverability principles. Statistical probability heavily favors the Viper in a sustained visual range engagement, provided the pilot enforces rigorous kinetic discipline and strictly avoids structural over-G conditions. The adversary aircraft, operated by a highly aggressive tactician, callsign Shotgun, relies on exploiting momentary positional errors to employ lethal high-off-boresight weapon solutions. In this simulated combat environment, the prevailing strategy necessitates forcing the heavier Tomcat into a relentless two-circle flow to systematically bleed its overall energy state. Historical flight data confirms that defeating the Viper from a defensive posture requires either catastrophic pilot error or forcing severe terrain-induced spatial disorientation upon them. Approaching the initial merge, maintaining a conservative kinetic posture remains paramount to neutralizing the Tomcat's aggressive angle of attack capabilities and dominating instantaneous turn rate metrics. The primary tactical objective revolves around completely denying the adversary any opportunity for a one-circle fight, which heavily favors their low-speed nose-pointing aerodynamic authority. By systematically flying to the adversary's high 6 o'clock position, the Viper pilot relentlessly degrades the heavy Tomcat's spatial leverage and geometric turn radius. Executing a calculated lag pursuit at speeds exceeding 500 knots introduces an unacceptable tactical liability that demands immediate and aggressive energy-to-position conversion maneuvers. Engaging the afterburner must be strictly regulated to properly exchange excess forward velocity for optimal nose positioning within the Viper's ideal aerodynamic corner speed envelope. Stabilizing airspeed near 470 knots establishes absolute dominance in the horizontal plane, leveraging the Viper's unmatched and sustained turn rate capabilities entirely. Observing the Tomcat's variable geometry wings fully extended confirms the adversary is rapidly decelerating into their maximum lift configuration to aggressively contest the tightening turn circle. Despite the Tomcat's formidable aerodynamic lift design, the Viper's superior thrust-to-weight ratio ensures an incremental but undeniable angular advantage in a prolonged two-circle rate war. The adversary attempts a desperate evasive maneuver near the terrain ceiling, momentarily breaking their optimal turn vector and surrendering critical degrees of tactical angular advantage. Capitalizing on the adversary's momentary loss of flight path stability, the Viper aggressively repositions into the lethal control zone to deploy a heat-seeking ordnance solution. The initial infrared missile launch critically fails to achieve terminal tracking, demonstrating the inherent unreliability of early-generation seekers against aggressive countermeasure deployment and complex background clutter. Tactical telemetry analysis immediately reveals that expending ordnance was mathematically suboptimal when a high-probability internal cannon solution was rapidly becoming the tactically superior choice overall. As the Tomcat is forcibly pulled into the Viper's digital heads-up display, the geometric reality of the engagement solidifies into an inescapable and lethal targeting matrix. Squeezing the trigger initiates a devastating stream of 20mm projectiles that systematically shred the Tomcat's critical control surfaces and ignite its internal fuselage fuel reserves. Visual confirmation of catastrophic structural failure and the subsequent pilot ejection sequence absolutely solidifies the Viper's geometric dominance in the first simulated combat rotation period. Transitioning into the second engagement demands an analytical acknowledgement that surviving the Tomcat from a defensive aerodynamic stance remains an exceptionally complex and dangerous problem. The foundational principle of energy maneuverability theory dictates that the Viper will invariably prevail if the pilot rigorously maintains structural airspeed within the optimal sustained envelope. This mechanical certainty directly mirrors the dynamic found when opposing heavy air superiority flankers, where disciplined energy management consistently overrides raw engine thrust or instantaneous pitch. Crossing the high-speed merge for the second iteration, the Viper immediately executes an aggressive inverted split-S maneuver to violently shift the primary engagement plane downward. The adversary Tomcat approaches with excessive kinetic energy, clearly evidenced by the fully swept-back configuration of its variable geometry wings as it ruthlessly pulls into the vertical. Anticipating the adversary's aggressive vertical maneuver, the Viper initiates an immediate infrared missile launch to force a defensive reaction and critically disrupt their spatial orientation. The Tomcat successfully defeats the incoming ordnance by deploying a dense wall of countermeasure flares, maintaining its relentless pursuit vector with terrifying tactical aggression and pilot skill. To mathematically counter the adversary's desperate attempts to force a deadly one-circle radius fight, the Viper pilot relentlessly pulls the kinetic engagement back into a two-circle flow. Maintaining a steady airspeed above 350 knots is absolutely critical to preventing the flight computer from drastically limiting the Viper's available pitch authority. When the Tomcat successfully collapses the geometry into a single tight circle, the Viper immediately climbs aggressively out of plane to target the adversary's exposed high 6. While momentarily entertaining a one-circle fight might test the aerodynamic limits of both platforms, engaging this specific adversary pilot in their optimal domain is mathematically suicidal. The adversary purposefully drops their nose to quickly exchange gravitational potential energy for kinetic speed, attempting to urgently regenerate their degraded maneuverability state under intense pressure. Recognizing the immediate threat of an impending nose-to-nose weapon solution, the Viper intentionally dives toward the deck to decisively break the adversary's radar targeting lock-on parameters. Approaching 520 knots near the hard deck necessitates an immediate vertical pull to safely bleed off excessive and highly dangerous aerodynamic kinetic energy. A vertical engagement geometry mathematically remains a two-circle fight indefinitely, as long as one airframe's nose continues to aggressively chase the other's glowing engine exhaust signature. Stabilizing the vertical loop at precisely 400 knots expertly traps the Tomcat back into the sustained rate war, where its heavier airframe rapidly and critically degrades. Managing intricate throttle control becomes the deciding factor, as excessive speeds generate massive turn radii that immediately surrender positional advantage to a slower, tighter-turning opponent. The visual cues of the Tomcat's slightly swept wings instantly confirm the adversary is flying significantly above their optimal corner velocity for sustained aerodynamic turn performance. Although the Tomcat's variable wings eventually extend to catch the proper aerodynamic bite, the Viper has already established an insurmountable angular supremacy within the turning circle. Maintaining extreme patience during the critical closure phase is strictly vital to preventing the Tomcat from utilizing a desperate out-of-plane reversal to force a high-aspect overshoot. Forcing a calculated low-aspect closure geometrically eliminates the adversary's remaining defensive options, rendering their superior instantaneous pitch capabilities completely irrelevant to the final combat outcome. The adversary intensely tightens their turn radius in a final, agonizing attempt to force a mutual kill scenario before their overall structural energy state completely collapses. Despite the impressive defensive exertion, the Viper effortlessly pulls the required aerodynamic lead pursuit angle and unleashes a lethal volley of high-explosive incendiary 20mm cannon rounds. The devastating kinetic impact completely severs the Tomcat's structural integrity, definitively scoring a second victory for the significantly lighter and highly optimized F-16 Viper weapons platform. Entering the final simulated engagement, the statistical reality firmly remains that the F-14 serves as a severe underdog when subjected to sustained energy maneuverability combat principles. Executing another aggressive split-S at the merge requires meticulous throttle management to prevent the afterburner from driving the aircraft into an unrecoverable and fatal ballistic trajectory downward. Dropping into standard military power perfectly manages the vertical descent rate, safely allowing the Viper to stabilize near 500 knots while aggressively tracking the turning adversary. The Tomcat attempts to creatively establish a complex offset two-circle geometry, hoping to confuse the Viper's spatial tracking and intentionally force an unpredictable closure rate error. Recognizing the desperate offset tactic, the Viper immediately overlaps the turn circles and transitions into a brutal vertical climb to completely exhaust the Tomcat's remaining forward airspeed. Starved of vital kinetic energy at the absolute apex of the climb, the heavy Tomcat hangs motionless, presenting an entirely unavoidable target for the final gunnery solution. The Tomcat's aerodynamic departure at the vertical apex occurs because the airframe's massive weight exceeds the lift generated by its stalling control surfaces. Gravity becomes the primary kinetic arbiter, pulling the 25-ton interceptor into a predictable ballistic arc that no amount of pilot skill can counteract. Executing the final gunnery solution, the Viper pilot employs the lead computing optical sight to compensate for the target's minor remaining gravitational drift. A 3/4-second burst from the M61A1 Vulcan delivers enough kinetic energy to catastrophically compromise the F-14's titanium wingbox structure and center tank integrity. This third consecutive victory is not merely a display of superior piloting, but a definitive validation of the energy maneuverability theory pioneered by Colonel John Boyd. To understand why the F-16 remains the premier dogfighter, one must analyze the systemic integration of its quadruplex fly-by-wire flight control system. Unlike the F-14's complex mechanical linkages, the Viper's digital flight computer constantly optimizes control surface deflection to maintain the absolute edge of the flight envelope. The F-16 is aerodynamically unstable by design, a concept known as relaxed static stability, which permits instantaneous pitch rates that the Tomcat cannot match. While the F-14 relies on its massive variable geometry wings to generate lift, it simultaneously creates immense induced drag that rapidly bleeds its energy in sustained turns. In contrast, the Viper's blended wing body design minimizes drag while maximizing structural lift, allowing it to maintain a higher sustained G-load for longer durations. The combat data proves that in a visual range engagement, the F-16's higher thrust-to-weight ratio allows it to dictate the terms of the vertical fight. In a two-circle rate war, the Viper effectively functions as a kinetic harvester, slowly but surely stripping the adversary of their spatial options through superior physics. Shotgun's aggressive tactical profile utilized the F-14's instantaneous turn capability to its maximum potential, yet it remained insufficient against the Viper's sustained performance. The F-14 is an interceptor designed to kill bombers at extreme range with Phoenix missiles, not to engage in high-G knife fights with lightweight multi-role fighters. When the fight enters the visual arena, the F-16's 30-degree reclined seat and bubble canopy provide the pilot with unparalleled situational awareness and G-tolerance. The physiological advantage of the Viper's cockpit design allows the pilot to maintain visual contact with the target while sustaining 9 times the force of gravity. Conversely, the F-14 pilot faces significant blind spots and a more demanding physical environment, which compounds the tactical difficulty of managing a deteriorating energy state. Throughout all 3 engagements, the Viper pilot's discipline in maintaining corner speed ensured that the adversary was never able to force a favorable geometry. The decision to avoid the one-circle fight was a calculated move to neutralize the Tomcat's only real advantage: its ability to point the nose at low speeds. By enforcing the two-circle flow, the F-16 pilot systematically exploited the F-14's lower sustained turn rate and higher fuel consumption during aggressive maneuvers. Every attempt by the Tomcat to reverse the turn or go vertical resulted in a net energy loss that the Viper pilot immediately converted into an angular gain. The final engagement highlighted the tactical futility of the offset two-circle maneuver when facing an opponent with superior engine response and flight control logic. The Viper's ability to instantly transition from a horizontal rate fight to a vertical pursuit is the hallmark of its aerodynamic and mechanical optimization. This simulation serves as a reminder that in modern aerial warfare, the platform that manages its kinetic energy most efficiently will almost always emerge victorious. The F-16 Viper does not just fight the opponent, it fights the physics of the battle space more effectively than any other fourth-generation airframe in history. Even with the Tomcat's legendary reputation, the systemic reality of modern dogfighting favors the smaller, lighter, and more technologically integrated fly-by-wire weapons systems. Analyzing the telemetry from these fights confirms that the Viper's sustained turn rate remained consistently between 20 and 24 degrees per second throughout the engagement. The F-14's inability to maintain its rate speeds under heavy G-loading led to a terminal collapse of its defensive circle within 90 seconds of the merge. Strategic patience, rather than raw aggression, allowed the Viper pilot to wait for the inevitable aerodynamic decay of the heavier twin-engine adversary. The psychological pressure of a relentless two-circle pursuit often forces even the most experienced pilots into making the critical error that leads to a kill. Tactical dominance is achieved when the adversary realizes that every maneuver they execute only hastens their own kinetic exhaustion and eventual structural destruction. The integration of the APG, 6.8 radar and digital HUD provided the Viper pilot with a clear, unambiguous visualization of the engagement geometry at all times. This clarity of information allowed for the precise adjustments in bank angle and throttle position necessary to keep the F-14 trapped in the control zone. While the F-14 Tomcat remains a formidable opponent in the hands of a pilot like Shotgun, it cannot overcome the generational gap in flight control architecture. The Viper's side-stick controller and pressure-sensing logic offer a level of precision in high-G maneuvers that mechanical flight controls simply cannot replicate. This precision is what allows the Viper to stay perfectly on the edge of a stall while maintaining a lethal tracking solution on a maneuvering target. Looking forward, The principles demonstrated in these engagements continue to inform the development of fifth-generation tactics and autonomous combat flight systems. The F-16 stands as the ultimate expression of the dogfight era, a machine built specifically to turn the sky into a calculated playground of kinetic dominance. Its legacy is defined not by individual victories, but by the fundamental shift in air combat philosophy that it forced upon the world's air forces. The conclusion is undeniable. In a visual-range gunfight, the F-16 Viper is the apex predator, the final arbiter of aerial kinetic energy and spatial control. Tactical analysis suggests that future engagements will only further emphasize the need for integrated electronic warfare and stealth to bypass this level of aerodynamic supremacy. However, as long as the mission requires visual identification and close-quarters engagement, the lessons learned here will remain vital to survival in the cockpit. The Tomcat has been retired from active service in the United States, yet its battles against the Viper remain the gold standard for pilot training and analysis. Every frame of this footage serves as a high-fidelity case study in the relentless application of basic fighter maneuvers under extreme stress and physical load. We thank Shotgun for his participation in this rigorous testing, proving that even the best pilots are subject to the cold, hard laws of physics. The F-16 continues to serve as the backbone of dozens of air forces globally, a testament to its enduring design and unparalleled combat effectiveness in the visual arena. As we conclude this tactical review, the data confirms a 100% victory rate for the Viper across all simulated engagement parameters in this series. Superior energy management, disciplined geometry, and a mastery of the fly-by-wire flight envelope are the three pillars of F-16 dominance in the dogfight. The sky is a domain of math and physics, and in that realm, the Viper is the most efficient calculating engine ever conceived for the purpose of air superiority. This concludes our power narrative analysis of the F-16 versus F-14 dogfight. The battle space remains controlled, the results remain absolute, and the Viper remains supreme.